So yes, this talk will be given by Rich Caruana. So Rich is senior principal researcher at Microsoft Research. So he did his PhD in CMU back in 90s. Maybe I'm guessing. So okay. So then after that, he was the faculty of in multiple universities like Cornell University, UCLA, and then CMU. And the interesting thing or the amazing thing is that his PhD topic exactly on multitask learning. So that has created a lot of interest for the subfield of transfer learning, because these days we see transfer learning is really a big area already. Maybe it was not that obvious back then. So today it's really like our honor to have Rich here to share his perspective, how this field has evolved during this last 20 years. So now the time is yours. Please go ahead. We are looking forward to your talk.
Great. Hey, thank you for the introduction, and thanks to the organizers for inviting me to talk at the workshop. So I'm thrilled to do that. I'm going to talk about some new ideas, some old ideas in deep multitask learning. Really, three things. I probably won't get to the last thing. The first is going to be really massive multitask learning, and this was an idea that's pretty old, but we didn't get it working until recently, and it depends on deep multitask learning to make it work. Then the second thing I'll talk a little bit about is a newer idea, which is intelligible and editable multitask learning using deep neural nets. And then I probably won't have any time to get to these tricks for making multitask learning work better. Fortunately, one or two of the tricks were already mentioned in earlier talks in the workshop, so you're really not going to be missing too much. Okay, let's jump in and talk about massive multitask learning. So, back in the 90s, after I was finishing my thesis in MTL, which I guess that finished in like 97 or 98, I was looking for ways to make multitask learning better. It worked well in many applications, but it didn't always scale to a very large number of tasks. And some problems that had a large number of tasks seemed kind of artificial. So I was looking for a real problem that naturally had very high task dimensionality, and where multitask learning was going to make the difference between success and failure, not just like a 1% or 5% increase in accuracy. I wanted it to be the game changer. So I thought about that. That's a hard problem. And then I thought about it some more. It's still a hard problem. I thought about it some more. Still a hard problem. And then I had an idea. And the idea is weather forecasting. So this first half of the talk, we're going to talk about weather forecasting using deep multitask learning. So, well, weather forecasting, let's think about it. I suggested that maybe we could predict weather on the entire globe at the same time. Now, if you just do 1 degree resolution on the globe, you've got 360 degrees around, 180 degrees above, that gives you 64,800 locations on the Earth. And by the way, 1 degree resolution is low resolution on the globe. So right away, if you wanted to predict the weather at each point, you'd have about 65,000 tasks. Now, at each point, you're actually interested in the weather at different altitudes, because atmosphere at high altitude is very, very important to weather at low altitude. At each location, you've got a bunch of things you want to predict: the temperature, the rainfall, the barometric pressure, the wind speed and direction, all sorts of things. So at each of these locations, you've got a bunch of altitudes. At each of those altitudes, you'd like to predict a bunch of things. And then, weather forecasting, we want to predict into the future. So, 8 hours into the future, 16 hours, 24 hours, 36, 48. So if you take all those things and multiply them together, you've got potentially somewhere between 10 million and 100 million output tasks. And that's for a low resolution grid. Okay, so this would be a pretty big network, okay, and it would have lots of outputs, right? We would have maybe 50 million outputs on this network. Now, the number of outputs would be 10 times larger than the number of inputs, and that's because the outputs are going to be all of these measurements at every point on the Earth for all possible times into the future that we're interested in predicting, whereas the input would probably only be the current state. So it would be all measurements at all altitudes, locations for all the variables, the current state. But from that, we would predict, all the future times that we're interested in. Okay, so that's kind of cool that the number of outputs would be, maybe 10 times larger than the number of inputs. Now, let's think about this. Let's say we're using a fully connected MLP. Well, and we're going to, let's say, 1,000 hidden units, right? This is a big problem. 1,000 hidden units isn't that big. Even back in the 90s, we knew we would need something like this. And now you've got 10 to 100 million output tasks. Just the last layer is going to have to be something like 10 billion to 100 billion weights. Okay. It's not feasible, right? Even today, we would have trouble training such a model. So we're going to have to depend heavily on convolution, which, by the way, is something I didn't know about in the late 90s. So we're going to have to depend on a trick that's a more recent trick. Well, actually, Jan had convolution in the late 90s. I just didn't know about it. And then we're also going to make another change. We're not going to predict for all different times at the same time. We're going to train a model that can just predict, say, 8 and maybe 16 hours into the future. And then we'll make a prediction of the model, feed it back into the model as if it was the current state, and then make a prediction for the next 8 and 16 hours into the future, take those predictions and feed it in. So now the model will make a prediction that's 3 or 4 days out, but it'll do that by getting applied repeatedly, iteratively to the inputs that it's predicted. Okay, now, the number of inputs in this new version is only going to be about 2 times smaller than the number of output tasks. And that's because what we're going to do is the model is going to predict the weather 6 hours into the future and 12 hours into the future. We found to make the model stable, we had to give it 2 different points into the future at least. We had to do some multitask learning even on time, or else the model wouldn't be stable. So now the number of outputs is about 2 times larger. And we'll do this roll forward that I was suggesting to predict the future. Now, hopefully you're thinking, this is a crazy idea, like predicting the weather, using machine learning. This really is a crazy idea. Weather forecasting is currently done via massive physical simulation on the world's largest supercomputers, right? So, and basically there have been 1,000+ PhDs over the last century that have built the physics and the models that are used in these physical simulations, right? So there has been a century of work by very smart physicists, people who know about fluid dynamics and all sorts of things, conservation of mass and all that sort of stuff. That's how weather forecasting currently works. So these guys have been doing an amazing amount of work. And I'll show you some of the early stuff that they've done in a few seconds. So how are we going to get machine learning to do this, right? Without physics. And it's really intense math. Like, how do we have a chance of getting something that's not going to know anything about physics to just do this using pattern recognition? Also, there's not much data. So, and then the weather and the climate, they keep changing. Like, we haven't seen all of the phenomena yet, right? We're talking about seeing 100-year events, in the weather the last few years. Well, the weather record doesn't go back far enough for it to include those 100-year events. So weather keeps changing in complex ways. Does machine learning really have a chance to do that? The beauty of physics is that it almost doesn't matter what the current state of the weather is and what it's going to be tomorrow, because if you got the physics right, well, then the physics will predict the correct thing because you can't violate the physics. Okay, but it's even worse than this. So weather data only goes back 20 to 40 years, depending on the quality of the data that you want. So it's not like we have a century of data. Now you think, there's 365 days per year. That's a lot of data. Well, it turns out if you take 40 years times 365 days, that's only 14,000, 15,000 days. That's not a lot of data for training a deep learning net. Even worse, if you think about it, every point on the globe, October 1st only happens once a year, right? The weather isn't the same, every one of those 14,000 days on the globe. So it's even worse. You only get like October 1st, October 15th, whatever, 20 or 40 times in the data set for each place on Earth. So, and the weather is very, very different from day to day and year to year. So this is really going to be sort of nasty as a machine learning problem. But why is this a good idea? And in particular, a good idea for multitask learning? Well, we all know that one of the places where multitask learning shines, and this is something we knew very early in the 90s, is when you have too little data to generalize well, where if you did single task learning, you wouldn't perform well because you wouldn't generalize well. But if you have many tasks which are correlated with each other, related to each other in some deep representational way, then you might actually do well by doing multitask learning. Well, that's what's going to happen. We don't have that much data, as in we've only got about 15,000 days, and October 1st at every place only happens 20 to 40 times in the data set. It's not enough data to train single task learning at any point on the globe. However, it is enough data for us to try doing multitask learning. And that's because points on the globe that are near each other have vaguely similar weather. Okay, so there's going to be a strong relationship between what we learn for this point on the globe and this point on the globe and this point on the globe. So that's going to be very, very important. So you could think of the globe as being a kind of map or an image. And our goal is to predict what the next state of that image is going to be, given the complex forces that are operating under the scenes. So that's what we're going to try to do. Now, back in 1998, I did a back of the envelope calculation, and I decided it's not going to work. At least it's not going to work yet. There was too little historical data back then. There was less than 20 years available. It's hard to get the data. We didn't really have GPUs. I didn't know if multitask learning with one hidden layer was really going to work. By the way, we all tried to make neural nets deeper back in the 90s, but we never really got much success or extra accuracy. Sometimes a second layer gave us a little extra accuracy, but by the time we got to 3 layers, we all struggled and really couldn't make anything magic happen. And back then, as I said, I didn't know about convolutional nets, and I knew it was going to be important for the neural net that was trying to do weather forecasting to know what pixels on the Earth were adjacent to other pixels, both in time and spatially. So I waited, I worked on other things. And around 2006, I started getting myself invited to the American Meteorological Society meeting. And I was doing work on ensemble learning that they were interested in. By the way, weather forecasters were some of the very first people to work on ensembles. So I went there thinking, okay, maybe the time is ready for this. I quickly concluded, no, it's still not going to work. 2016, I got an intern at Microsoft Research. This is an intern really good at deep learning, really good at applying deep learning to science problems like chemistry, physics, things like that. And we tried hard to get weather forecasting to work with deep multitask learning. And we sort of never got it to work. I'll give you an update on that in a second. But part of the problem was we didn't know about weather. And it turns out you really do need to know about weather to get this to work. We actually had parts of it working better than we thought, but we were using the wrong metrics. So in fact, weather forecasters use very sophisticated metrics that are carefully designed to their problems. And they're like, we would try to predict temperature or rainfall, and weather forecasters are like, oh, no, that's secondary stuff. What you really need to predict is the pressure at 500 hectopascals. So it's really interesting. Like weather forecasters immediately think different things are important than what we thought. To me, weather was what's the temperature tomorrow? Is it going to rain? Is it going to be cloudy or sunny? The weather forecasters see that as, oh, that's a secondary effect. You have to learn the primary effects before you can learn those secondary things. Okay, so we failed in 2016. We didn't publish any papers. 2018, I went to the UW, University of Washington, atmospheric sciences chair, and I proposed this project on weather forecasting. And he said, you're crazy. It's never going to work. And he said, but we're interested in machine learning for weather forecasting. You want to work with us? And I said, great. So we started some collaboration. There were some grad students at that first meeting. One of those grad students named Jonathan Ween, great grad student, by the way, he's graduated now. We hired him at Microsoft. He thought it was an interesting idea. He's a meteorology grad student. He was taking a machine learning course where he was learning about deep learning. He had to do a project for the class. He has access to the data. He knows how to do weather, like, that's his specialty. And now he was learning machine learning. So he gave it a try. And I got a call from the dean saying, that crazy idea you had, it's working. Jonathan tried it for a class and it's working. Let's start working on this together. Okay, so now I'm going to start using some slides that I've got from Dale, who's a professor at UW. Jonathan Ween is the grad student who this became Jonathan's thesis. So in fact, if this was a different deck, Jonathan would be the first author here since he's done most of the work. Nathaniel, Jonathan's graduated. Nathaniel is a new grad student who is picking up the work now that Jonathan has been hired away by Microsoft. And then this is, I got to admit, these guys all know about weather forecasting and simulation. They really understand this stuff. I know about machine learning and multitask learning, but I know very little about weather forecasting. So my only contribution here is on the machine learning side. Okay, so let's jump in. Even back in the 20s, this guy, Lewis Richardson, had this crazy idea that you could use math to predict the weather. And he imagined a huge room filled with human computers who were each working on a part of the math in order to make predictions for the weather. And each one would work on their piece, and then their piece would be handed to somebody who integrated the pieces, and eventually that would become a weather forecast. Now, by 1950, Jule Charney and von Neumann actually did the first experiment using a computer to do this. So they used the ENIAC computer. And remember I said, weather forecasters are smart. They don't go after like directly predicting temperature or rainfall or anything like that. What they do is they predict the 500 hectopascal surface. This is what's the altitude at which the air pressure is this. It turns out that's the most important part of the atmosphere for weather forecasting. And then they treat this all as a very complex set of differential equations. So to them, it's all fluid dynamics, conservation of mass, conservation of energy, and things like that. Now, the interesting thing is it took the first experiment, it took the computer about 24 hours to compute a 24-hour forecast. So it means it would have actually been easier to just wait for the weather to happen. But at least this was a real first attempt at making these sorts of predictions. So now the interesting question is, can you trust these physical models? Well, these models have a lot going for them. They really know a lot of physics. So they know all sorts of things about conservation. They know how fluids work. So they really take this physics deeply, and they have very well-tuned physical simulations of this physics. And then for things that aren't really expressible as physics, like heat transfer, they do empirical models of those things, like empirical models of the effect of the sun on the surface and clouds and things like that. It's hard to get that with pure physics. And they combine these models that use deep physics with some simpler models that are more empirically based, but still not machine learning for the most part. Now, we're going to do this with AI, right? So we're going to try to learn a model. By the way, these state-of-the-art models require the world's largest supercomputers. But what we're going to do is we're going to throw all of that away. We're not going to do any simulation at all. And we're just going to try to train a deep multitask neural net to do this from the data. And if we can do that, it'll take a lot of time. Like, they don't have to train the physical simulation. Well, they did. It took them a century of PhDs to train that model, to write the physics and create the physical simulations. We're going to have to train a model from data. That's actually going to take us a lot of time. But then our model is going to be really fast at runtime because it's just a feed-forward neural net, whereas their simulations actually really had to do a lot of work at runtime. So, and here's what the Earth is going to look like. Instead of using a globe, things get very close to each other when you get to the poles. If you're doing latitude and longitude, they use what's called the cube sphere. So they're going to break the middle 60 plus or minus degrees of the Earth into 4 square faces, and then they'll have a square face for the north region and the southern region. And this is important because the winds blow in different directions and different things happen there. And then in the convolutional net that we're going to use, most of our filters are going to be 3x3 filters. We're going to use these polar faces. And then this is what our model is going to be. We've gone through many variations on the model. This is a UNet architecture, which is pretty well known now in deep learning. And this model is important really for 2 reasons. One, The top path gives us detail, and then the bottom path gives us better generalization. And one of the interesting things about weather is that it's a local phenomena and a global phenomena, and you can't like only model it one way or the other way. You have to do both of these. So we needed to get a deep neural net to do both of these. So it turns out that by going down to this lower resolution, we get information at larger scales happening down here. But by keeping these layers at the top, we get fine scale information. It turns out all of that is critical to making it work at a global scale. So this is roughly what the model looks like. We've played with many variations of this model. The most important thing is at the bottom, we've managed to get it down to just about 2 to 3 million total learned parameters in this model. And that's very important. If we let the thing get too big, it turns out we don't have enough data to train it. And it's critical that this is a convolutional net. There's no way to do this that I'm aware of with an MLP. Okay, so the model training, we're going to use data from 79 to 2012. So that gives us about 100,000 samples. The validation set will be the next few years, and then the test set will be the last few years. And we can test twice weekly in what we're doing. This is when we train the model. The blue line is the training loss, and the red is the loss on the validation set. And there's pretty good correlation there. We have a little bit of jumpiness in the validation loss, but it's not too bad. And then at the very end here, we do some very fine tuning that suddenly causes the model to get a little bit better. So overall training is reasonably well behaved once we got it all working. And training is all happening on a single GPU, a single like V100 GPU. And as I said, it takes about a week to train this model. Now, we've got a number of variables. We have what's the altitude for 1,500 hectopascals? What's the thickness of the high pressure region? We've got the temperature at 2 meters. We've got the water vapor, things like that. And then we also know things such as where's land and sea, because it turns out weather is very, very different over land and sea. We know the topographic height at different places, and we know the incoming solar radiation. Because that changes from day to day, right, as the sun moves. Well, really as the Earth moves in its orbit around the sun. Okay, and the resolution we're using is 64 by 64 points on each face of that cube. This is a low resolution visualization here, and that gives us about 1.4 degrees by 1.4 degrees at the equator, a little finer resolution as we go further north. And I just want to show you, here's the model running for 4 days. So I'm going to hit play here. So watch the model. This is the forecast just after 6 hours. The right is ground truth. That's the real weather. The left is the prediction of our model. So that's really pretty good. Whoops, let me go back and play that again for you. It's not perfect. There are differences. Notice that this is slightly different from this. This ridge here isn't exactly the same, but man, this is a really, really good forecast. Okay, now here's the important thing. I'm going to compare our model now to the world's best weather forecasting model, which is the European model, ICCV. It's an ensemble of models in the European model. NOAA recently updated their computers and soon should be able to compute models that are hopefully as accurate as ICCV. But right now, ICCV is the world's best weather forecasting model. Our model, which is deep learning weather prediction, well, our horizontal resolution is 150 kilometers, whereas the physics simulation is almost 10 times the resolution. It's 18 kilometers. We've got only a few inputs like where the sea versus land is. They have many, many things in ICCV. We only have a small number of 2D variables. We don't have all the measurements throughout the whole altitude. They have all of these things for many different vertical levels. So they have much more detailed information. We don't have any of these helper models that are coupled to the model, whereas they have many helper empirically derived models. They do a lot more work to vary the initial conditions to train their ensemble, but our model is faster, so ultimately we can compute more members of our ensemble, and we do that by perturbing the weights in our model as well as the inputs in our model, whereas what they do is they play with the physics and make it stochastic. Okay, so their model has a lot more information than we currently can afford to incorporate into our model. And that's partly because, training on a single GPU can't handle all of this, in part because the memory just gets too large. The data set becomes too large. Also, it takes a lot of work to incorporate all of these things and then to do what tweaks you have to do to make the model work. This is the first comparison. Let me show you this. This is a root mean squared error. So down is good on this plot. This is time on the x-axis. So this is 2 weeks on the right here. This is 7 days in the middle. Gray is climatology. That just means predict at that point what the average weather has been over the last 40 years at that point on this day. So whatever the weather was here in Seattle on October 1st, the last 20 years, just predict that's what's going to happen again. Turns out that's pretty good in Seattle because it's always raining on October 1st. But in most places around the earth, this would not be very good. So climatology, and we use climatology actually as a correction to the other terms. It becomes the baseline. So that's why it's a flat line across all weather forecasts. Then notice that persistence, that's this pink line. You just predict that the weather tomorrow is going to be the same as the weather today. And that's not a bad forecast for 1 day out. 2 days out, it's not as good. By the time you're 7 days out, that's worse than climatology. It'd be better if you just predicted what happened a year ago today, as opposed to predicting what happened 7 days ago. And that's because the weather changes over time. Now, the ECMWF ensemble, that's this red line. Okay, so this is currently the most accurate model on the planet. We are this green line. And the truth is, we're not doing too bad. We're not doing too bad in at least 2 different ways. Well, 3 different ways. One, we're never too far from the ECMWF model. We're 2 to 3 days behind. The other thing is we always do better than climatology, even after 14 days. By the way, it took weather forecasting a long time. Only recently did they get to the point where their models were better than climatology after 14 days. And then notice in the very beginning here, there's a chance that we're actually competitive with or even better on very short timescales. Here's another metric that they use, and it tells basically the same story. In this graph, up is good. And again, persistence in this case is a little better because of the way it's defined than climatology, whereas it was worse here for long timescales. But again, we're not doing too bad, and we don't have any of the many benefits going into this ECMWF model. And the difference is in, say, for a 1 week forecast, the difference is about 3 days. We're about as accurate, at 5 days, by the way. But it's an amazing thing. And it turns out if you just were to go back 10 or 15 years, ECMWF would have been about 3 days behind what it is currently now. So we're only about 10 or 20 years behind what the best ECMWF models have been doing. This is yet another graph. And what's really important here is notice this goes out to days 15 to 21. That's 3 weeks, 4 weeks, 5 weeks, and further. And the green and the pink are ECMWF and us. And notice that we catch up with ECMWF when we get to 3, 4, and 5 weeks. That's very important because it turns out this is an important time scale for things like agriculture and other things. Basically, being able to predict what the weather is going to be like in a month is very, very important for many uses. And weather forecasting has struggled to do this well. And our model is now as good as ECMWF for doing that. It's really, really very impressive. I'll skip that. Basically, we're now working on precipitation. It turns out precipitation is actually one of the hardest and most important variables in weather forecasting. And we're just working to try to make our model better on precipitation. We're using the same variables, but we've changed the way we train the model a little bit. And we're trying to use it to come up with better deep learning precipitation forecast. There's a chance we can revolutionize things. So it turns out the largest supercomputers in the world are necessary to run ECMWF, but we're able to do a full 1 week forecast with an ensemble of 320 models at 6-hour resolution. We can do this using a single V100 GPU. and we can do a single time step in 1/10 of a second. We're just incredibly fast. So this means these ensembles can be really, really large. There's also an interesting possibility that we might be able to combine our forecast with the forecast from ECMWF and do something that's better than either of these alone. By the way, we've got 3 papers now that have been accepted in James, the Journal of Atmospheric Sciences. This is the main journal for weather forecasting. And the work is getting some nice attention. We're getting actually some recognition and awards for the work. So, hey, we're not yet as accurate as the best models. They're still 2 to 3 days ahead of us. NOAA is not quite as good as ECMWF yet. So we're actually closer to NOAA than we are to ECMWF. But we're only about a decade behind what these models were able to do. And we've only been working for a couple of years as opposed to a century. And our spatial and temporal resolution is much smaller, and we don't use half of the variables that they use. So it's really impressive that we're sort of even in the ballpark, given what we're doing. But we're thousands of times faster, and we're competitive at this 3 to 6 week timescale, which is really, really important. This is exciting stuff. It's really audacious to try to replace all this physical simulation with just multitask learning. It's impressive that it's working as well as it is. And we think combining these models with the physical simulation could be the best of both worlds. But for now, we're going to keep focusing on making this multitask learning model as good as possible. And I think just by giving it more inputs and outputs, it's going to do a better job as we can afford to train the model. Okay. So it's kind of working, and that's really exciting. All right, so I'm going to spend a little bit of time talking about this other topic, and then that's it. I'll wrap up. So this other topic is going to be interpretable deep multitask learning. This is a new stuff we've been working on, and it uses deep learning. Okay, so this is a collaboration with a number of people, some from Google, some from Microsoft, Jeff Hinton from Toronto. And this is a paper that we're just publishing this year at NeurIPS. So this is going to be neural additive models. So let me give you an introduction to what's called generalized additive models. You might have heard that there's a trade-off between accuracy and intelligibility. Deep neural nets are black boxes. They're really accurate, but they're not intelligible. Things like linear regression and stuff like that are intelligible, but they're not very accurate. The good news is that if you're playing with tabular data, sadly, tabular data is not images. Images are pixels. But if you're playing with tabular data where you know what each feature means, that's like blood pressure, age, stuff like that, this trade-off is no longer true. So in the last 5 to 10 years, we've been able to train models called EBMs, which are just as accurate on tabular data as these other full complexity black box models. And they're even more interpretable than these simpler models. So let me give you an idea what these generalized additive models are. Well, here's linear and logistic regression. These things are interpretable, but not so accurate. They can't handle nonlinearities. And in particular, in healthcare, they can't model things like, well, you're healthiest when your body temperature is in the middle at 36 to 38 C, but you're less healthy if you're cold or if you're hot, if you're feverish, right? A linear model can't model those things. Now, at the right extreme here, we've got black box models. This is like a deep neural net. It's not interpretable typically, but it can be very accurate. It can handle nonlinearities and can handle these normal effects, although it's more likely to learn spurious things. There's this class of models in between that statisticians invented 40 years ago called generalized additive models, and EBMs is our version of this. And these things are much more interpretable actually than even linear methods, but they can be as accurate as these black boxes, and they can model nonlinearities and things like this, and they're less likely to show spurious effects. And here's just some experiments we did. Here's 10 data sets. This is AUC, so up is good. The average AUC of the EBM is 0.866. This is a fully interpretable model. And yet here, the most accurate model wasn't a deep neural net. It turned out it was gradient boosted trees that were regularized in depth. And we're matching the accuracy of those models. So we're not more accurate than those models, but we're equal accuracy, but we're fully interpretable. Here's an experiment by Cynthia Rudin. She does a lot of work in glass box learning. And in her experiments with her students, it turned out we were the most accurate interpretable model. And she also observed that these interpretable models were about as accurate as the best black box models. Okay, how do you train these EBMs? No neural nets yet, Okay, we haven't gotten to multitask neural nets yet. So what do? This is boosted trees. We train thousands of trees that can only use feature one. Each tree can only use feature one. Another thousands of trees that can all use just feature two. And we do this in a cyclic boosting fashion. We go from feature to feature to feature, keep adding trees to the model. Eventually we have thousands of trees, but these trees can only use feature one. Turns out you can summarize all the trees that just use one feature by a graph of their average response for that feature. And you can do that for the next feature and for the next feature. Eventually, you've got all of these boosted trees. This now could be millions of boosted trees summarized by these graphs. You don't need the trees anymore. The model is now a summation of what has been represented on these graphs. Okay, so that's generalized additive models. This algorithm I just described is currently the world's best algorithm. Well, now that we have NAMs, it's not the best. It's tied perhaps for the best. But for the last 10 years, this has been the best algorithm for training generalized additive models. So there are problems though. Hey, half of the world doesn't use boosted trees. They use neural nets. And these things don't scale. Boosted trees are harder to get working at high scale on GPUs, whereas neural nets are easy now to make work on GPUs. And it turns out the GANs trained with boosted trees, they're not differentiable, and that reduces their flexibility. And neural nets are a lot more modular and flexible. I'll show you examples of that. And it's hard to get things like multitask learning actually to work with boosted trees, but easy to get it to work with neural nets. So there are lots of reasons why we would want to train these models with neural nets. So here's how we do that. So here's feature one, feature two, feature three, or feature K. Each of these features goes into a deep, wide subnet, but that subnet can only look at this feature, and this subnet can only look at this feature. So each of these subnets, which is part of a large deep neural net, can only look at one feature at a time. And then the output of these nets is summed, and if we're doing classification, goes through a sigmoid. So that's important. So this is an additive model. It's additive in these subnets. Each of these subnets is itself a deep model. So the sum of all these things is a deep model. And what happens is after you've trained this model, you can take this entire subnet and you can do what we did with the trees. You can replace it with a graph by looking at its IO behavior. And that means this subnet becomes a graph for feature one. This subnet becomes a graph for feature two. This subnet becomes a graph for feature X sub K. And now you have an interpretable, editable, additive model, but you've trained it with deep learning. And the beauty is this thing is differentiable. We can do multitask learning and stuff like that. There is a problem, which I won't dwell on, which is it turns out we often see when we use EBMs that models like to make jumps. Like here's a jump in risk at 85 and a drop in risk at 100. Here's a rise in blood pressure risk at 175, at 200, and at 225, and then the risk comes down. These are jumps in risk. This is a really important drop in risk that happens. This is PF ratios, a measure of how well you're breathing. Turns out that's a critical drop in risk happening right at that point in the graph. Turns out neural nets are a little too smooth, and they don't like to learn these rapid transitions as well as decision trees do. Decision trees, if anything, are learning too rapid transitions. So we see jumps like this all the time. And what we had to do is we had to modify neural nets with a new loss function, a new hidden unit loss, so that they could be jumpier. And then to prevent them from overfitting, which isn't as big of a problem in these additive models, we would do an ensemble of these things. Let me just show you the empirical results. It's working. These NAMs are as good on these classification data sets as EBMs, which were the state of the art. And they're, in this particular case, on classification, they're actually doing as well as deep neural nets would have done. On regression, we're not quite as good as deep neural nets. We're very close. And once again, these NAMs, these neural additive models, are as good as the EBMs. So that's great. So we've got it working. You can now train GAMs with neural nets, or you can train them with boosted trees. Now, I'm going to skip that. Let me show you how we can benefit from differentiability. This is a complex model that we're using in healthcare. This is a single task neural additive model that can only see the medications the patient took before they came to the hospital and the lab tests early in the hospital. And it is trying to predict the risk of this patient of dying without seeing any treatments. This is a multitask neural net. I'll show you how we do that in a second, that sees those inputs, but it also gets to see the inpatient medications, the treatments that these patients are seeing. And the goal of this model is we want the top model to predict raw risk of the patient without treatment. And we want the bottom model to only learn what is the benefit to the patient of the particular treatments that we're receiving. If we train just one model to predict all of mortality risk from all of these features at the same time, it doesn't end up separating patient risk from treatment. And this is just some examples. At the bottom here, this is patient's age. And what you see is anticoagulants, NSAIDs, glucocorticoids. Hey, they're all more beneficial for younger patients than for the sicker older patients. That's to be expected. On the top, though, we're looking at neutrophil lymphocyte ratio, and it's interesting. It turns out that anticoagulants and NSAIDs are most beneficial for young patients. But when we get to a treatment like glucocorticoids, that's more beneficial for the older patients. So, and it turns out this has led us to do many other studies, and it is affecting how care is being delivered in hospitals. So let me show you how we do multitask learning with NAMs, and then we're done. So this is a single task NAM. Remember, it's a single subnet for each feature. What we're going to do is have multiple output tasks, right? So this is 3 tasks here. And just notice that each one is fully connected to each of the subnets. So this first subnet, which is learning from feature 1, now has to try to learn some representation, some graph that's useful for all 3 tasks. There's a limitation to this, though, which is that it turns out it has to learn the same graph for all the tasks. Now it can do weird things, like it could put a 0, like task 1 could put a 0 weight and ignore this graph, or it could put a negative weight on it and actually invert the graph. But it can't learn different shapes to the graph if necessary for different tasks. So instead, what we're going to do is we're going to have multiple subnets, all learning from feature 1, multiple subnets, all learning from feature 2. And then each output task will have multiple weights to each of those subnets. And now if it wants, if 2 tasks really need a different graph for feature 1, they can decide, well, you'll use the first 3 subnets, I'll use the last 3 subnets, and they can learn different graphs. If they want the same graph, they can have similar weights to all of the subnets, and they can basically learn a small ensemble of these graphs. So it really lets them learn separate graphs when they need to and learn identical graphs when they need to. I'm going to skip the synthetic experiment, but this really works. This is a compass recidivism problem, which is we're trying to predict the chance that a person in criminal justice will commit another crime. And here's the beauty. Single task learning on the left, okay, has to learn the same graph for each one of these features. However, multitask learning on the right, if we break the problem up into learn a separate a GAM model for women and a separate model for men, it turns out there are some cases where the models do learn somewhat different subnets. So for example, here's the whether the original conviction was a felony or not. And it turns out there is a reasonable difference between men and women when it's a felony degree. And then this is a race, looking at whether there's bias in the model. And once again, there is reasonable difference here. And yet for other graphs, like some of these things on the left, say age and prior counts, it turns out they're essentially identical for men and women. So this is really, really working. Okay, so here's a summary of this part. Glass box learning really can be as accurate as black box learning on tabular data, and it can also be editable. These NAMs now let us train these GAMs using deep neural nets, which is great. It makes them differentiable. It lets us do architectures like that personalized medicine architecture that we could never do easily with the boosted tree model. And these things can really scale now to massive size. And we have a toolkit that makes it easier to train these models. That'll be available soon. You can already train the boosted tree ones. That's been available for a couple of years. The neural net one should be out in a couple of months. And we think there are going to be many opportunities to combine this deep learning with neural additive models with other things like regular deep neural nets, convolutional neural nets, reinforcement learning, inverse reinforcement learning, and all those sorts of things. Okay, I was going to go into some tricks, but I think we've run out of time, and that's fine. These tricks tend to be old things that applied as much to shallow networks as to deep networks, and I think we don't need to go into those. So let me just stop the presentation and say thank you.
Yeah, thank you very much for the very like mind-opening talk. So these are really, I think they're very really game-changing work. So thank you so much. So we are looking forward to see your model deployed to the like the real like world like weather forecasting stations.
Cross your fingers.
Yeah,
that's our goal,
exactly.
but that's probably 5 years away. So yeah,
we will see it. So for sure. So okay, so are there any questions from our audience? Like, well, yeah, for Rich, yeah. So
I actually have a quick question.
Go ahead.
Sure, go for it.
Which is, this is a very naive question, but I believe that DeepMind released a paper recently about weather forecasting, and I'm curious if you can comment on like the accuracy or any sort of comparison there between the models you've been training and their model.
Right. There is other work now that's being done on using deep learning. Well, first of all, machine learning has been used in weather forecasting for many, many years, but not the way we're doing it. We're doing something crazy. We're going to ignore the physics and just treat it as a pattern recognition problem. Weather forecasting hasn't tried to do that. As I said, when I went to the dean of UW's weather forecasting department, they just said, that's a crazy idea. We're not going to do it. And then a year later, we started focusing more on it. Most of the other papers that you'll see on machine learning and deep learning for weather forecasting are trying to do one of two things. They're either trying to help with these auxiliary models that are as much empirical as they are physics, things like solar radiation and how it gets through clouds. That's something they don't really have accurate physical simulations of. So they do that sort of empirically. So machine learning is used a lot for those sorts of things. The other thing is you'll see a lot of the weather forecasting that's being done with deep learning is it's called now forecasting. It's like you're trying to predict, is it safe for me to go for a walk in 2 hours, or will I get rained upon? And they're deep learning. Remember, I showed a comparison between us and ECMWF, and at very short timescales, we were equal to or better than ECMWF. And that is like the easy place for deep learning to be competitive. And often what people do is they really treat, for example, rainfall forecasting as a image tracking kind of problem. They look at the radar and then they learn to predict what the radar will look like in 5 minutes, 10 minutes, 15 minutes, 20 minutes. They learn to predict that. And then from that, they read back what the forecast would be. So there is interesting stuff that's being done, but we're the only ones crazy enough so far to try to throw away the physics, work from the raw data, just take a training set and try to train a model from beginning to end to predict all of these things. And it's taken some work, but we do have it kind of working best now at this surprisingly long term. We thought it would work best at the short to medium term, but it's actually proving to be a valuable model in this seasonal to seasonal term, this 3 to 6 week kind of forecast. Sorry, that was a long answer, but yeah. The other work that's being done, by the way, is very good. It's very nice work.
Mm-hmm. Yeah, thank you very much. So yeah, I think in the interest